It's not.
Is there a reason it's not Diet Pepsi?
I don't drink Diet Pepsi. Hi everyone, this is Kelsey. I'm in a group with Cameron and Jackie, and we'll be going over Urysohn's lemma. So I'll pick up the first part of the proof, and they'll pick up after me. So you'll be seeing them in a bit. So Urysohn's lemma essentially asserts the existence of a certain real-valued continuous function on a normal space X, and it's used to prove the TT extension theorem and Urysohn's metrization theorem, which other groups are going to be proving. And so this proof of this lemma is actually referred to as deep and original, and so different books, our book for our class calls it a hard proof, or not in the sense that it's difficult, but it's like a concrete proof, whereas other textbooks actually do refer to this proof as being sort of not intuitive and very original, and they actually refer to this proof being like not everyone can just come up with it on the fly. Not an average topology student could have come up with this. So it does mention that someone very, very bright, which Urysohn was very, very bright, came up with this proof. So within this proof, we'll need to know what a dyadic rational number is and what normal is, and so we'll go over that. But so the lemma states that E and F are disjoint closed subsets of a normal topological space X, and then that means that there exists a continuous function f from X to the unit interval 0, 1, such that f equals 0 on E and f equals 1 on F. Okay, so let's go ahead and get started with the background. So a dyadic rational number, which we'll be using, is a rational number of the form p over 2n, where p and n are in the integers, and dyadic rationals are dense in R. And we'll also need to recall what it means to be normal, because X is a normal topological space. So a space X is normal if for each pair E and F of disjoint closed subsets of X, there exists disjoint open sets U and V such that E is a subset of U and F is a subset of V. So in this proof, we are going to want to construct, using normality, a certain family UR of open sets of X that are indexed by the dyadic rationals. And then we use these sets to define the continuous function F. So some textbooks do use the actual rational numbers instead, and I think that dyadic rationals are just an easier way to bookkeep sets, so that's why we're going to use them here. So first of all, as in the theorem, how it states, E and F are disjoint closed subsets of a normal topological space X. So I'm going to say, let E and F be disjoint closed subsets of a normal topological space X. Okay, so we're going to go ahead and let V equal X without F. So V is the open set such that E is a subset of V. So V is going to be like our first kind of open set that we're going to have. And we have that V is open because F is closed. So as a picture, we kind of have something that looks like this. We have X here. Then we have these closed subsets E and F. And then I'm going to let V is essentially everything but F here. So the highlighted stuff. If we don't get that little piece in F. That's basically V. Okay, and we notice that E is actually contained in V. So to build this family, we're going to use Lemma 5.2. So Lemma 5.2 states that a topological space X is normal. We have X is normal, so we're going to go ahead and use this. If and only if for each closed subset E of X and each open set W containing E, there exists an open set U containing E such that the closure of U is contained in W. So that's just like a lot. And so I feel like it's good to do like a little baby example of what this is saying and then expand it essentially out to a larger inductive process that we could take on. So we're going to say by Lemma 5.2, there exists an open set U sub 1/2, so 1/2 is actually a dyadic rational, containing E such that E is a subset of U to the 1/2, which is a subset of the closure of U, which is a subset of V. And note that this is just kind of like by closure properties. Okay. So we have essentially V is like our W from the lemma. And then, so this is like W from the lemma here. And then the U to the 1/2 is like the U from the lemma. So we would have X is normal. So for each closed subset E of X and each open set V containing E, there exists an open set U to the 1/2 containing E such that the closure U to the 1/2 is contained in V. So that's the direct application of Lemma 5.2. So that's just kind of to get a feel for it. And now we're going to essentially kind of induct this process. So I'm going to induct it a bit just to get a feel for what that induction would look like. And then we'll just keep on going. So I'm going to go ahead and apply Lemma 5.2 to the open set U to the 1/2 containing E. So in that case, our E is going to be like our closed set E. And then the U to the 1/2 is going to be like our W. And then there's going to be the other case where V is going to be our open set. So V is going to be like our W containing the closure of U to the 1/2. So in that case, like that's going to be our E. And then we're going to get open sets U to the 1/4 and U to the 3/4, which are going to be our W. So I have E. Let me do this in a different color so it stands out. So I have E is a subset of U to the 1/4, which will be a subset of the closure of U to the 1/4. And then that's contained in U to the 1/2. Okay, so in this case, I'll put it in red. We have that like our E is like our E from the lemma, so I'm just going to use the lemma's notation. Here, U to the 1/2 is like our W, and then U to the 1/4 is like our U from the lemma. So essentially we have, for each closed subset E of X, and each open set U 1/2 containing E, there exists an open set U to the 1/4 containing E such that the closure U to the 1/4 is contained in U to the 1/2. So there's that case. And then there's also the case where we have the closure of U to the 1/2 is like our E, and we have that by closure. This subset inclusion holds. So U to the 3/4, the closure U to the 3/4, and then we have V. So I'll just draw like a kind of little line here to separate. So here in this case we have like our E is the closure of U to the 1/2. V is like our W, and then the U is like U to the 3/4. And I'll go ahead and write W equals V here, so we have all the things from the lemma. So I'll have here like our W equals U to the 1/2, and then our U equals U to the 1/4. Okay, so like the lemma, we have that the closure of U to the 1/2, and then each open set V containing the closure U to the 1/2, there exists an open set U to the 3/4 such that the closure U to the 3/4 is contained in that V. Okay, so essentially from there, that's just how it's going to look for the rest of the way. So continuing essentially in this way, in an inductive manner, and we could do this since the dyadic rationals are countable in 0 to 1. We have, for each dyadic rational, are in 0 to 1. We have an open set U sub R in X such that these three things hold. So we have first that the closure of U to the R is contained in U to the S, where our R is less than S, and those are going to be between 0 and 1. Second thing is E is going to be contained in U to the R, or U sub R. This is for R between 0 to 1. And then our third thing that we have is U to the R is contained in V. And that's for R between 0 to 1. So these three things we could kind of pick up from based on the concrete subset inclusions that we were looking at earlier. And so notice that the sets UR are ordered by inclusion in the same way that their subscripts are ordered by the usual ordering on the real line. So that's why we use the dyadic rational, so we could kind of like order them in a logical sense numerically, because 1/2 is greater than like 1/4 and so on and so forth. So the picture of this kind of ends up looking something like this. So we have, remember we have our set X, and then we have our closed sets E and F. And then we have V is kind of just everything without F. And so when we're building our sets, we have like U to the 1/4 here. And then U to the 1/2 contains that U to the 1/4. And then we have like U to the 3/4. And so we can see that we keep getting closer and closer and closer to f. And then each of these u's is contained within the next. Okay, so I'll go ahead and pass it on, and we'll pick up from there.
So picking up where we left off, we've got this diagram here, space X with two closed subsets, E and F, which are disjoint, and X is normal. Now, we found in the last section that we can find any number of open sets, each of which is contained in the next one, and all of which contain E. So you've got E, and then U 1/4 being an open set around it that contains E, and then U 1/2 being an open set that contains U 1/4, and then U 3/4 an open set containing U 1/2, so on and so forth. And so that's, for this specific example, or this diagram that we have right here only shows those, but in theory we could add as many of those as we wanted for every dyadic rational. So an infinite number of these concentric open sets. And so now we're in a position to define the function that we're interested in, which is the function that returns 0 whenever you're in E and 1 whenever you're in F. So the way we're going to do that, well, the actual definition of the function is as follows. If the value of X that we pick is inside of all of the concentric open sets, which essentially means that it could be written like this: f of X equals 0 if X is an element of UR for all R greater than 0. So what we're saying here is that if X is in all of the URs, then its value is f of X is going to be 0. And really all that's saying is that if you pick a point, for example, in the diagram we have so far, if we let this be X, then since it's contained in U 1/4 and it's also contained in U 1/2 and it's also contained in U 3/4, it's contained in all of those, so it's just going to be 0. Now, if we had infinitely many of these open sets, each containing each other, it would have to be inside of the open set for the smallest dyadic rational, which means it's basically inside of all of them. All right. So if X is not inside of all of them, we define it as follows. F of X is equal to the supremum of the R's for all of the URs such that X is not contained in them. So what does this mean? It means that if we pick a point X, so I'm going to get rid of the X we had before. Suppose we pick a point X over here now. So it's inside of U12 and U34, but it's not contained in U14. Then the value of X would be the supremum of the sets which do not contain it, which is 1/4 in this particular case. Again, however, if we were to extend this to have an infinite number of these open sets corresponding to each dyadic rational, each of the value of X would be kind of wedged in between the set that contains it and the smallest set that contains it and the largest set that does not contain it. And so that's going to become a narrower and narrower region as you add more dyadic rationals. So the reason we're constructing the value or equation for f like this is because that way, if you have x, if your value for if x is inside of E, if x is over here, then even if you've got an infinite number of open sets, x is contained in all of them. X is going to be contained in UR for any value of R, because even for the smallest values of R, E is contained in UR. So that forces x to be 0, since it's contained in all of them. And on the other extreme, if x is inside of F, well, none of the URs intersect with F. F is fully contained in X. Let's do it like this. F is contained in X without UR for all R. So given that, if x is in F, then x is not in any of those open sets UR, and since R ranges from 0 to 1, x is the supremum of the dyadic rationals between 0 and 1, so x is 1, which is what we want. You can kind of visualize this as, in the example currently drawn, you can visualize it as a series of steps. So if you're anywhere in E or 1/4, the value of F is 0. So if you're anywhere in here, the value of F is 0. If you are in this middle region, in between U1/4 and U1/2, so contained in U1/2 but not contained in U1/4, then the value of x would be 1/4. If you're in the next region out, the value of x would be 1/2. And if you're outside of U3/4, then the value of x would be 3/4. But, so that doesn't quite get us where we need it to be, but that's because there's only 3 sets containing each other at the moment. If you had all of the dyadic rationals, then you'd basically have an infinite number of infinitesimally small steps taking you from f equals 0 when you're anywhere in E to f equals 1 when you're anywhere in F. And intuitively, that sounds like something that would be continuous, but we will prove the continuity of that function in the next section.
That was so good. I gotta watch it again. Okay, hello. So now, continuing on in our proof, we just have it left to show that f is continuous. So if we want to show that f is continuous, we're going to consider all x in R space x. And we have 3 different cases for x. Case 1 is that f of x is equal to 0. The other 2 cases are going to be that f of x is equal to 1, and the third case is when f of x is between 0 and 1. But let's just start with our first case for the time being. If we have f of x is equal to 0, we know that from the definition of our function that x must be in E. And in order to show that our function is continuous at this point x, we're going to come up with a sequence of xn's that are going to approach x. Then the limit of f of each of these xn's is going to be equal to f of x, which we know from assumption is equal to 0. And so this is saying that our function at x is equal, or when f of x is equal to 0, it's continuous. And then our case 2, when f of x is equal to 1, is just similar to our first case. So now that we showed that the endpoints are both continuous, we're going to consider case 3, where f of x is in the open interval from 0 to 1. And just like many continuity proofs, we're going to start with let epsilon be greater than 0. We're going to pick dyadic rationals R and S, and we're going to pick them such that R is greater than 0 and S is less than 1. And then we're also going to pick them such that f of x minus epsilon is less than r, which is less than f of x, which is also between s and also between f of x plus epsilon. Okay, let's draw a picture so we can better see what we're talking about. Well, we have our closed set E, and we have our closed set F somewhere over there. And this X, since it's in between, or this X, because f of x is in between 0 and 1, its corresponding set U is going to look something like this. We're going to call it U sub f of x. And then we're going to go ahead and draw U sub r so that it is containing E, but it is also contained in U of f of x. And we're doing this right because R is less than f of x, so that means that the corresponding open set U is going to be smaller than the corresponding set U for f of x. And then on the opposite side of that, our U sub s is going to contain all of those sets, and it's going to be somewhere out over here. Okay, so you can see from the picture pretty clearly that x is not in U sub t, where t is a dyadic rational between R and f of x. Right, because Rx is somewhere over here. It is right up to the edge of our U sub f of x, and we're saying that x is not going to be in any sort of U that is between U sub R and U sub f of x. Okay. And so we can also say from this that x is not going to be in the closure of U sub R. But it's pretty clear that x is in U sub S, right? Because x is still on the boundary of this U sub f of x, which is contained in U of s, or U sub S. And then if we let this new set W be equal to U sub S without the boundary or the closure of U sub R, we know that W is open and it contains X. Right, and so W is all of this red marking right here. So it's everything in between the boundary of U sub R all the way up to U sub S. Okay. So let's consider a y that's in W, so that's the red portion of our picture. Then you can see pretty clearly that R is less than or equal to f of y, which is less than or equal to s. And that's because, right, our y is going to be somewhere in the red portion, so somewhere over here. And so our function, when we put y into our function f, it's going to spit out a number that's greater than the r because y is not contained in U sub r. And it's going to throw out a number that is smaller than s or equal to s because y is contained in U sub s. So this gives us the equation that is very similar to from before, right? We have f of x minus epsilon is less than r, and then we just found out that r is less than or equal to f of y, which is less than or equal to s, which from before is less than f of x plus epsilon. And let's simplify this a little bit. Let's get rid of the r and the s. And so we're going to get f of x minus epsilon is strictly less than f of y, which is strictly less than f of x plus epsilon. All of this is to say that f of y is somewhere epsilon away from f of x. And so rewriting that, we can just say that the absolute value of f of x minus f of y is less than epsilon. And this is true for all y in W, which means that f is continuous on the open interval from 0 to 1, and since we also showed in case 1 and 2 that f is continuous at 0 and at 1, we can say that f is continuous at x. And that completes the proof.